let me start by thanking you for the introduction and also for the invitation to this wonderful meeting. And my talk is about, as you said, parametric post-processing of dual resolution precipitation forecasts. And it is based on a recent publication that I had with my thesis advisor and one of his colleagues. And also it is part of my PhD dissertation. And so just to give you a brief introduction about all of the different definitions that lies in the title, let me just go through on the topic, on the base of weather forecasting. So when we think about weather forecasting, we usually think of a numerical prediction, so a value that comes across from our news, from wherever. You can see a nice picture on the left-hand side. And so it is just a value for the different weather variables. Now, this is a deterministic forecasting method, and it is based on usually the physical and chemical models of the atmosphere. But as we know, there is some limitations to this, and it is not always perfectly precise. And so there are not enough data available. We do not know precisely the state of the atmosphere at any given time. That should be the starting point for all of these methods. And also the methods contain some estimation themselves. And so that hinders the methodology. And so to counter this, in the 90s, a lot of major weather prediction centers have started using and utilizing a so-called ensemble forecast, which is a collection of weather predictions. And they run these models, or one model with some slight perturbations in its initial conditions or parametrizations. They run these, and with this collection of output, they call that an ensemble. And so with this, now they obtain, which is the advantage of this method, they obtain and it provide an estimate of the uncertainty of the forecast. But of course, as with every methodology, there are some downsides, which is that a usual problem with ensemble forecasting is that it can be under-dispersive, and there is still some bias in the output. And so some form of calibration is needed. In terms of calibration, what I mean is that there should be a consistency between the probabilistic forecast and the relative frequency of the observations that we have. So let's talk a bit more about, and starting to get into the data that I had access to. So as I said, a lot of major prediction centers have been operationally using this methodology, and one of the largest ones in Europe is the European Center for Medium Range Weather Forecast, which ECMWF for short, which had, at the time that I was able to start working on this and around this topic, they had, as an operational ensemble system, they had a one higher grid resolution member in their system and one control with 50 members from perturbed analysis. So 2 levels of resolution. Now, in terms of the resolution, what I mean is the grid resolution at which they are providing the forecasts at, and they are calculating all of the model results. And so the denser it is, the smaller the number for the resolution, the better, the more precise it could be. Now, of course, this means that also the computational cost rises with the grid resolution going up. But they, of course, want to increase their model grid resolution even higher to 5 kilometers. And this is in their strategic plan. But the problem is, as I said, that the cost ratio between the then operational and the 5 kilometers is quite high. And so their proposed solution was to try to analyze and try to obtain some results with regards to a dual resolution ensemble system. And what this means is that they would have in their system different combinations of higher and lower resolution members. And so what we need to understand with this is that the computational cost is proportional to the number of members. And of course, it is also proportional to the cube of increase in resolution. So we might want to have as many members as we could possibly have, and also as high resolution as we possibly could have. But of course, the lower resolution members have a smaller cost. So we could have, the idea is that we could have more of them with the same cost, and we could have a smaller amount with higher resolutional numbers. And so the aim is that they fixed a computational cost in regards to their then operational system. And they wanted to set with the same exact computational cost, we wanted to set the different combinations to try out and to analyze whether they provide a better predictive performance in terms of calibration, of predicting better results and better fitting to the observations. Right, and so trying to find this optimal combination can mean a lot of different things. So they have started with some preliminary results in terms of temperature forecast, dual resolution temperature forecast. And I was able to join the research at this time, around 2018, I guess. And I was able to join with my supervisor in terms of not just seeing and analyzing the properties of this raw, so-called raw dual resolution temperature forecast, but also calibrating it. So as I said, it needs some sort of calibration, these forecasts, these ensemble systems. And so we tried to approach this with the side of calibration. And there's also another side and also another route, which was about precipitation forecasts. So it's also with dual resolution, with the same kind of combinations in dual resolution, but there was some results obtained by the third member of our authors list that I just showed on the first slide. She or they did as a group a non-parametric quantile mapping approach in terms of calibration and calibrating the precipitation forecasts. And our proposed experiment was to do almost the same thing, but we wanted to compare the different calibration methods. So our methodology includes parametric approaches. And so that's what I will be talking to you more about. So on this slide, we can see right on the right-hand side, the map of our data. Now that is only the observation station. So those are around 2000 or some more stations in Europe that we had precipitation data from. But the gridded data that the forecast is based at, and with the different resolutions, contains around 300,000 different points. And so we needed to have the corresponding connections made between those based on location. And so here you can see the investigated configuration. So as I said, even though they want to have this 5 kilometer grid resolution established, they do not, or at least they did not have that at the time. And so what we and the other researchers were able to test all of this theory on was just with 18 kilometers set as our high resolution and 29 kilometers set as our low resolution ensemble members. And so we had 50 of the higher resolution and 200 from the lower one. So as we said, or as I said before, the fixed cost is the same for 50 members of just the higher resolution one and 200 of the lower one. So those are with the same cost. The ratio, as you can see, is not the same as we would have with the 5 kilometers one, but it's still substantial enough to test and worth to test. And so here you can see in this table the different combinations. So we tested 5 different ones. With on the left-hand side, you can see just the 50 purely high resolution combination. And on the right-hand side, you can see the 200 of the lower one. And in between, we have a mixed, 3 mixed combinations. So the data set, as I said, consists of 24-hour precipitation accumulation data. And we have the corresponding verifying observations. Now, it's important that the previous study that I mentioned with non-parametric approaches in terms of calibration used a much longer time period to train their models on. They had 20 years of historical data. And the comparison to that is not just about using a parametric approach, but also to try to train our model on much shorter interval. So what we had was just 97 calendar days, with also the stations are set to be the same, just to have a direct comparison to that. Now, the hardest part about the precipitation data is that a lot of it is zero, right? So not in terms of temperature, which would have a lot of different varying data points, but 50% or more than that of our observations were zero for each lead time. And as I said, and to try to show you in a visual form that the data needs calibration, so we do not need, or we cannot just rely on having the raw data, the raw ensemble as forecast, we need to apply some sort of calibration. So as you can see here, this is a verification rank histogram. It shows in a histogram form the ranks of the verifying observations with respect to the corresponding ensemble forecast. And so you can see here that it's very U-shaped. It should be more uniform. And so we need to use some sort of calibration. Now, one of the main ones to use is a statistical post-processing approach, which means that we want to improve our future predictions by fitting a suitable model to the forecast based on previous predictions and, of course, the corresponding validating observations. And the parametric approach that we used was the EMOS, the Ensemble Model Output Statistics, which fits a single probability distribution to the ensemble forecast with the distribution parameters depending on the ensemble members. So this could be even just an ensemble mean or the individual members or whatever we can come up with. Now, of course, different weather quantities require different predictive distributions, so it needs to be suitable for the weather quantities properties. And so, for example, for temperature or pressure, we would use a normal distribution, which fits quite good. But for precipitation, we need to take into account its discrete continuous nature. And so it needs to be a non-negative predictive distribution that can assign positive mass to the zero precipitation event. And so what we have chosen here and what is proven before for precipitation accumulation is a continuous distribution that can take both positive and negative values, but we censor it at zero from the left. And so, for example, what we used here was a shifted gamma distribution left censored at zero. Here you can see all of the parametrization for it with its shape and scale and also the shift parameter. But it can be also defined with its mean and standard deviation, which on the last row, you can see that it's all dependent on the means of our high and low resolution numbers and components of the forecast and their overall mean. So that is what we based our model on. And the model itself is trained, and during the training process, it needs to calibrate or calculate, the A, B, H, B, L, and C and D parameters. So overall, those are the ones that we need to optimize for. Right, and so going forward with the model fitting, so as I said, to estimate these parameters, these 5 parameters, we need to optimize over the mean value of a proper scoring rule. So this is set in the literature, and the most widely used proper scoring rule is the continuous ranked probability score, or CRPS for short. And as you can see here, it includes the predictive CDF that we have chosen and the verifying observations. So we are trying to see the difference there. Now this, to be able to numerically stably compute this, we need a closed form for this formula. And so that needs to be given for all of these different distributions, which thankfully we already had that from previous publications. So for the CSG distribution, we already had a closed form, so we could calculate with that. There's also, in terms of validating the model that we have trained, we can use the CRPS as well, but there's also different kinds of prior score and quantile score and so on. We cannot go into detail much more on that for the lack of time. But there's also skill scores that we can calculate, which is in terms of, they're calculated in terms of reference forecast. So we can compare to, in terms of this specific score, we can compare it to a reference forecast score. And as you can see from these two formulations, the CRPS itself is a negatively oriented score, so the smaller, the better, but the skill score counterpart is a positively oriented score, so the higher, the better. And also, I will be briefly mentioning the PIT, the probability integral transform, at the end of the slides, because it will be a counterpart to the previously shown verification rank histogram for terms of row ensemble, just to look at how it stands up in terms of consistency, and the probability integral transform, which will also show in a histogram form, means that we can see and evaluate the value of the predictive CDF at the verifying observations. And so it will also show, or hopefully it will show, a uniform distribution, so that it shows that it had the desired calibrating effect. So let's move on to the training data quite quickly. So we had, there are a couple of approaches to train the model with the data. So as I said, we had quite a lot of stations. So there is around Europe, so there is quite a large variability in terms of climate and so on. I'm not a meteorologist, but this is just from common sense of looking at the map. And so there is a local approach, which means that for every station, we train the model separately and obtain parameters for that station. But that leaves us with a very small amount of data, just that 30 days or however many we choose to train specifically, and still leave a lot of it for validation. The other part, or the other approach, is a global approach, which means that we estimate all of the parameters are estimated with all of the data. So all of the stations come together to do the estimation. But that is also not applicable here because we have so much variability, as I said. And so there is a middle ground, which is a semi-local approach, a clustering-based semi-local approach, so that the stations are clustered based on their training data in various ways. And then we are applying the global approach on the clusters. Right, and here you can see some results. So as I mentioned, here we have the CRPS, which is, as I said, the smaller the better. With the yellow lines, you can see the model that we have applied. With the blue, there is the raw uncalibrated version. And so every calibration is outperforming that one. On the right, you can maybe try to see the differences between the different combinations. And so there is not a lot of difference. We could look at the differences between the combinations, trying to find an optimal one in terms of just the CRPSS, so the skill score. But as you can see, there are quite large margins of error here, like quite large confidence intervals for this. And also the differences between the different combinations are not significant in our case. So this means that the post-processing also took out the large differences between the combinations in terms of comparing it to the raw one, but also our approach has decreased these differences even more. And so just lastly, I wanted to show you the PIT histograms. This is for just one of the lead times, but it shows for every combination we tested, it shows a much more uniform shape. And so the calibration worked in itself. That was one of the results. So to conclude everything, we have significantly improved the forecast scale compared to the raw ones for all lead times and thresholds, and also found that there is no significant difference in the different scales for the combinations. But what the original aim was to compare it to the other quantile mapping non-parametric approach with the longer training data, with 20 years of training data, we were able to catch up to that with just using much smaller data set, and also the validation was on the same one, so it was a fair comparison. But we were able to catch up with that. And for our future research, we want to be able to apply all of this information that we have found and all of these results in terms of the newly obtained and generated dual resolution ensemble with the new resolutions, and maybe even try out some machine learning based approaches. And I would like to thank you for your attention. And here is the information regarding the publication.
Thank you for the interesting presentation. Is there any question? Yes, Zhikica?
I'm sorry, I was muted. Actually, I wanted to ask, was there any analysis done for the wind data, probably in Central Europe or something like that? Because wind is a huge factor in there.
Yes, right. So in regards of the dual resolution, I don't believe that they have, but probably working on it with now the new cycle with the new resolution data. I myself have not been worked on. Well, I have not worked on wind dual resolution forecast, but single resolution, yes, not precisely in Europe, but it is quite a it has a quite big impact on all of the different ones. But we usually don't combine, or I haven't combined different weather variables to try to supplement data with another variable. So, for example, we haven't supplemented wind into precipitation, if that was what your question was aiming at.
Okay, thank you very much.
Thank you for your question.
Andrei?
Thank you. Thank you for a nice presentation. So your approach is parametric as compared to non-parametric.
Yes.
Are there significant advantages? Maybe I missed something. And if you plan to extend this to machine learning, commonly machine learning is also connected to more non-parametric approaches. Where do you expect to extend it and how to balance between this distinction?
Right. Thank you for the good question. So the first part about why this was a good aim to start out, well, mainly for the shorter period of time, so that if they are not able to apply a methodology that needs that big amount of data, then we should turn to ones that can handle shorter times. That was one of them. This is an easier, or it requires smaller computational costs, I guess. I haven't tried for myself out the quantile mapping approach, but I heard from the third order that it was quite intensive to run. And also the advantage to the non-parametric one is, of course, that they don't need to choose a distribution. As for ourselves, we needed to choose one. So it's a limitation for the parametric one, that we need to set a suitable one. And what if it's not suitable for that data? So there is a disadvantage here as well. In terms of, yes?
No, just please continue, please.
Oh, okay. So in terms of the machine learning, what we have already tried to accomplish, and there's also already literature about this from my supervisor, is also a combination. In terms of the machine learning, we combine the distributional effect, and we also base it on the distribution. So the machine learning itself is, of course, inputting. We have the input as the ensemble members, maybe the mean, for the different resolutions, or just the standard deviation, or whatever. Or maybe we can even supplement with some other data. And the output is the parameters of the distribution. And so not the calibrated forecast itself, and comparing that to the observation, but the distribution parameters. So we are taking out the parameter estimation part of the EMOS of A, B, H, B, L, and C and D, and we are only focusing on the parameters. So we don't need to think of the link functions between the members and the parameters, but just focusing on trying to use the machine learning to estimate the mean or standard deviation of the location and scale of the distribution.
Okay, thank you. Thanks.
Thank you.
Okay, I have a question, technical one.
Yeah.
Since you have censored distribution for estimation of the parameter, did you use some estimator for censored data? For example, when we don't use, in that case, empirical distribution function, we use Kaplan-Meier estimator.
Oh, I see. I haven't actually, but we also, I'm fair to mention that I also estimated not just the A, B, C, and D, but also the shift parameter, and so we have used that. So it's another one to be estimated with the CRPS, but I haven't tried. anything else out.
Okay, and did you use some other distribution than gamma? Or just
Not in
gamma?
this, not in this case, not in this case, but there are a lot of other distributions for precipitation as well that can have a good effect. But this was the most recent one in terms of the EMOS, so that's why we have chosen this one.
Okay, thank you.